So 1920s, we've got the Serbian geophysicist Milutin Milenkovic. And what he started studying was, well, this just says nothing ever changes, right? And he said, well, if we start really paying attention to astronomy, right? So he started looking at how the Earth interacted with the sun. What he discovered was there are some aspects with the way that the Earth moves that are cyclic, right? Meaning they repeat in these cycles. And with a cycle, we talk about the periodicity, right? How long it takes, time-wise for one cycle to complete. And he really looked at three different things. And so let's dip into those for a second. So the first thing that we think of as these Milenkovic cycles, and there's really three primary components, is he discovered the eccentricity, the eccentricness, right? The out of roundness of Earth's orbit. And it turns out as Earth, so this little dot that I've got here is the sun, the way that the Earth travels around the sun changes over time. Almost like a breathing pattern, if you'd think about it like that. So it's kind of out of round and closer to round, and out of round and closer to round, which means that over that time, that actually changes the amount of incoming solar radiation. The Earth's eccentricity operates Earth's eccentricity operates with a period of about 100,000 years, meaning that's how long it takes to go from one stage out of round and then kind of back to where you began, right? So it's about a 100,000 year cycle. So the next thing that Milenkovic worked out, the next Milenkovic cycle, is essentially the amount or the degree of Earth's tilt. So Earth has a rotational axis, and that rotational axis actually varies by a few degrees over time, meaning as it's rotating, it's kind of moving back and forth a little bit. That rotational axis kind of wobbles about 3 degrees. That has a periodicity of about 40,000 years. This last one is a little bit more difficult to draw, and it actually has to do with the direction that the axis is pointed, meaning the direction the Earth's rotational axis is tilted slowly changes over time. But you can actually see this with a top, right? If you spin a top like a child's toy, the top itself is spinning really quickly, but very slowly the axis of rotation of the top will spin, but it's also at a constant rate. I mean, constant as, the top is slowing down. So it's got a deceleration. But that precession would be the axis of rotation very slowly changing while the top itself is spinning really quickly. And so that operates with a periodicity of a little bit more than 2,500 years. Let's call it 26. And so collectively, these three, eccentricity, tilt, and precession, we kind of bundle those together as Milenkovic cycles. So when we put all of these together, because each of them change incoming solar radiation, when we stack all of these Milenkovic cycles on top of one another, they actually show how solar radiation should change over the long term. And it's, roughly every 20,000 years, but it's not even that clean. And what we found is that Milenkovic cycles do a great job, right? We see increased glaciation when it should be. We see decreased glaciation when there should be. So really, these are the kind of the primary driver for variable climate over the kind of, tens of thousands of years time scale. So Milenkovic, 100 years ago nailed this stuff, which was pretty awesome. So where does this fall apart? So first of all, Milenkovic, great job, worked all of this out. What he didn't really account for, so all he's looking at it, and if you think back to these EBMs, right, these energy balance models, that's where he shines. But those don't capture all of the variables. And so going back even further, right, so his work was done in the 1920s. There was work done in the early 1800s. So 1807 is the first time that someone coins the term the greenhouse effect. They didn't fully understand what was causing it. But again, thinking about initial thoughts of energy balance, people realized there was something that was holding heat back, right? Energy was coming in, energy was sticking around for a while, and then energy was leaving, right? So the idea that there was some force in the atmosphere that was holding heat in, that's a 200-year-old idea. That's over 200 years old. So take that, 90 years later, 1897. It was like horse and buggy days, right? 1897, before the car, before the airplane, there was a very famous paper. There was a very famous paper published that said, "Hey, we're burning coal as energy to keep our houses warm. That coal releases CO2, and guess what? We discovered CO2 is the primary thing in the atmosphere that's holding in heat." And so, again, over 100 years ago, almost 130 years ago now, these scientists said, if we keep inputting CO2 in the atmosphere, I think the Earth's going to get pretty hot. So the Earth's temperature is a function of how much CO2 there is in the atmosphere. And actually, not long after that, everyone said, oh, no, you're wrong. It's the water vapor. But kind of putting it all back together now, we realize the water vapor is in the atmosphere because of CO2, right? So really, this notion of the greenhouse effect, this notion of carbon in the atmosphere as the primary driver for temperature is not new at all. And that's where we start to see, the energy balance models start to fall apart, because you have to have these other variables, right? You have to have, well, how does CO2 change over time? Because we can't just take, what's present in 1897 and run with it, right? So that variable has changed significantly over time. So we have to build much more complicated models. We have to go back to those GCMs, those initial global circulation models, or again, on the modern world, global climate models. And those help us change those variables, right, that we now know need to be included if we're going to accurately predict the climate. Okay, I'll catch you in the next video.